Thank you, Leslie. Next, we'll be hearing from Jodie Wall on Washout Solutions. Jodie Wall has worked in Inorganic Ventures Quality Control Department for more than 8 years, making her proficient in ICP OES, ICP mass spec, ion chromatography, and the various titration techniques used at IV. She has a BA in chemistry from Virginia Tech and has years of experience in water quality and environmental testing, as well as other manufacturing laboratory settings, such as custom DNA plasmid design and sequencing. I will now turn it over to Jodie.
Hello, I'm Jodie Wall, and I am the Quality Control Supervisor here at Inorganic Ventures. I've been working in the QC department here for almost 10 years, so I've had lots of experience troubleshooting several different ICP systems, both OES and MS. In particular, the troubleshooting I'm going to talk about in today's presentation revolves around rinse solutions and strategies to mitigate ICP washout issues. Some of the elements that you run through your instruments are what we refer to around here as sticky. This means that you may experience washout issues and memory effects. There are a few symptoms to watch out for. You may notice that the intensities of your blanks are much higher at the end of your run than they were at the beginning. And if you dig into your data a little, you may notice that the intensities get progressively higher with each injection of the sample. In extreme cases, you may even observe the quantifiable presence of an element in a later sample where there really shouldn't be any. There are a number of things that can cause these issues. Some elements have a certain affinity for the plastic parts of your instrument. Sample matrix and composition can also complicate matters. Rinse solution and rinsing protocols in your method can play an important role, and the components of your introductory system can add to washout issues as well. Most of the elements that we work with at IV are stable in a nitric acid matrix, but there are some exceptions. This can be important to note, as an element in its ideal matrix should have an easier time of staying in solution and hopefully present fewer washout issues. Some elements, such as tungsten and silicon, require hydrofluoric acid for stabilization. Some elements require hydrochloric acid for stabilization, and an example of that would be low-level mercury. The tricky thing to be aware of when combining elements in solution is that some of the elements may not be compatible with HF and/or HCl. For instance, silver, in the presence of HCl, can have photosensitivity issues and precipitate as silver chloride. And adding HF to your matrix could cause issues if you are analyzing boron or silicon. On the other end of the spectrum, there are also analytes to consider, such as bromide and iodide, that require a basic matrix for stabilization instead of an acid. Some elements are soluble in HF and require it for long-term stabilization. You will see these elements in yellow on the periodic table here. There are some elements that are highlighted here in orange that will steal the HF from those elements that require it to stay in solution. When the orange elements are combined with the yellow HF elements in a solution, you will likely find that a higher concentration of HF is required to keep everything happy. Then we have the elements shown here in red, which need to avoid HF for long-term stabilization. If you're experiencing issues with washout or memory effects with any of these yellow HF elements, we recommend adding HF to your rinse solutions to help keep them moving through the system. On this version of the periodic table, the elements highlighted in blue require an HCl matrix for stabilization. You may recognize the elements in green as being HF elements from the last slide. While HF is the preferred matrix, these elements can work without HF, but it may require a higher percentage of HCl than usual. The elements shown here in red need to avoid HCl for long-term stabilization. Mercury in particular can be a pain for many analysts, and we have definitely had our fair share of mercury issues in our lab. At low levels, and by that we mean typically under about 200 parts per million, you may start to see issues with mercury sticking to plastic when only nitric acid is used. If you add HCl to your diluent and rinse solutions, it should help mitigate these absorption issues. However, there are a couple things you'll want to consider there. The first one is the other elements in your sample and their compatibility with HCl. One example of how this can be a challenge for ICP mass spec users in particular is that introducing HCl will cause issues with an argon chloride interference on arsenic. Another thing to watch out for is that if you start to see false high readings for mercury, you may be seeing the effects of diatomic mercury. Allowing your samples and standards to sit and equilibrate may help this. In our lab, we have seen an improvement letting things sit anywhere from overnight and even up to a week in extreme cases. Another possible option to mitigate mercury adsorption in nitric acid is to add 1 ppm gold to the preps as part of the matrix. And another thing you may want to try is glass introsystem parts as opposed to plastic. Some analytes prefer a basic environment, and those include the light blue elements in this particular periodic table. Bromide and iodide generally work well using a triethanolamine and ammonium hydroxide rinse solution. The elements highlighted in purple here, again, may look a little familiar to you as they were originally yellow HF elements. While HF is the preferred matrix, these elements can be used in a basic solution, but the addition of any acid will cause them to fall out of that solution. Boron and arsenic can also be analyzed in this type of environment, but here at IV, we typically analyze these in acidic matrices. So all the elements shown here in pink are commonly observed to cause headaches with washout and/or memory effects. Reflecting back to the most common reasons for washout issues that we listed, the next thing we're going to do is to start to examine why each of these has that kind of a problem. Understanding that can help us make a better decision about how to alleviate that problem. So why are these particular elements difficult to rinse out of the system? Here is a sort of overlay of all the matrix interactions we just looked at on the previous slides. The yellow HF elements can be difficult to wash out without the use of HF. For the orange elements, nitric acid alone may not be sufficient to remove everything. HCl can help with some of these orange elements, but you'll see in blue that this can cause issues for silver, possibly causing the precipitate I mentioned earlier. A safe approach to having both HCl and silver in solution together is to keep your silver low and your HCl high. Usually a 10 ppm silver solution requires about 10% HCl for long-term stabilization. We understand that this is too high for some analytes, and if that's the case, the HCl can be decreased through a little bit of trial and error until you observe an acceptable usage period. Keep in mind that these solutions are light sensitive. Once the silver precipitates, it can be difficult to remove the solids from your system. In our lab, we sometimes go so far as to wrap the sample tubes in electrical tape to try and cut down on some of that light exposure, especially if we're setting up a large set of samples and the prep might sit a little bit before it actually hits the instrument. The stickiness of the elements in pink may be related to their oxidation state. However, we have not really had a chance to research that very well in our own lab. Matrix selection aside, let's now look at some of the other ways we can try to curb washout issues. Good solution design is a great place to start. If your calibration or check solutions have more elements than you need, it may be worth investigating whether some of those extra elements are causing these types of issues for you. It may be easier to just remove them. There may be a different stock offering that meets your needs, Or you may find that a custom standard that only contains the elements you need is the best approach. If you have any questions on the best sample matrix, please feel free to reach out to our chemists anytime. Another step that is crucial when dealing with washout is developing effective rinse strategies. Some instrument software will allow you to program sample or global rinses right into your method. They can go right at the end of each sample, or you can put a really big rinse at the end of the entire run. Some will allow you to monitor a rinse in real time. We actually do this on one of our instruments on a daily basis to make sure that our tuning solution has all been rinsed out before our first analysis of the day. We simply run our instrument rinse solution while monitoring a particular wavelength until the intensities reach what we have set as our low threshold. Another strategy is to run rinses as samples, inserted into the sample list where needed. This also allows you to troubleshoot a little, as you can run various solutions in various orders to find the most effective option for your situation. Here we have an example of how those strategies can be used involving a 100 ppm boron solution in 0.1% nitric acid. The wavelength 208.959 was monitored, and here you can see the overlaid results of both a 5% nitric acid rinse and a 5% ammonium hydroxide rinse. On the left side of the image, we start with the high leftover intensities from the sample, and over on the far right, both rinses do eventually reach the baseline. So we can say that both of these solutions do rinse boron from the system. However, if you take a look at where the lines start to curve, you can see that there is a little bit of a discrepancy there. So we're going to take a closer look at that. This is the bottom part of that graph blown up so you can see the rinse results a bit more clearly. It is more obvious here that the black line, which is the nitric rinse, has still not made it fully back to the baseline after 2 minutes, while the green line, which is the ammonium hydroxide rinse, reaches baseline within about 80 seconds. So we can conclude that the ammonium hydroxide is a more effective rinse solution for this particular situation. Now you have a couple of ways that you can use that information. One thing you could do is you could insert tubes of ammonium hydroxide rinse into your run after sticky boron samples. Or another thing you could do is prepare a 5% ammonium hydroxide bottle and have it on hand and use it as a rinse when you start to see the problem happen. Your intro system is another place to look when troubleshooting washout issues. Peristaltic pump tubing is an example of one of those plastics that some elements like to stick to and can contribute to the problem. If you are using pump tubing to deliver your sample, you may want to consider changing your tubing daily, or even possibly changing directly after a run that contains sticky elements that you're having trouble with. There are also intro-system add-ons you could investigate that allow your sample to bypass the pump tubing. These include things like syringe drives and injection valves. Let's take a look at some recipes for common rinse solutions and their general uses. Usually, the more robust OES systems can handle higher percentage solutions than the more delicate MS systems. That's why you can see here that 5 to 10% nitric, or HCl, is common for OES, and for MS, those percentages are kept at 1 to 2. Another common option that we use in our lab quite a bit is a 2% solution of a detergent, such as RBS 25. As you can see, there is a caveat on the RBS 25 solution, as it does contain high amounts of sodium, making it not very applicable to mass spec. Another thing to watch out for there is that RBS is pretty basic, so you may want to try adding a water rinse before your system sees any more acid to avoid any issues with salt buildup. Also keep in mind that very caustic solutions can degrade your system, which is another reason we stick with the 2.5% as a rinse. Some elements even work well with just a DI water rinse. such as sodium, potassium, and calcium. We have talked about elements that may need an HF solution to wash out, but HF rinse solutions also carry some special considerations. If your intro system or torch contain glass, limit your HF to a maximum of 0.2%. If boron or silicon happen to be elements of interest in your analysis, know that these will probably read unreliably and on the high side, as HF will leach them from borosilicate glass. Matching the amount of HF in your standards and samples may help mitigate this effect. If you have an HF-resistant intro system and torch, you can take your HF percentage up to between 2 and 3% as a maximum limit. However, you don't want to go too crazy because these systems are HF-resistant, not HF-proof. So they do still get degraded over time, and the higher the percentage of HF you use, the more quickly you're going to see that happen. Now let's take a look at some rinse solution recipes that are helpful in more specialized situations. Earlier I demonstrated how an ammonium hydroxide solution can be useful when working with boron. It can also be helpful for bromide, iodide, and mercury. 1 to 5% should do it for both OES and MS systems. A 10% HCl and 0.5% hydroxylamine chloride solution can be useful when dealing with osmium, and a mix of between 1 and 10% HCl with 0.5% thiourea can be helpful in dealing with osmium, mercury, and gold. We recommend keeping various rinse solutions on hand as they can be used in many ways in different situations. For instance, they can be used as rinses, or as diluents, or as matrices. This is a picture of an actual rack in one of our auto samplers. As you can see, we've taken the solutions that we use most often, and we've put them into nice little color-coded bottles, and they're right there at the fingertips of our techs when they need them. In review, here are IV's recommended washout solutions listed out for both ICP, OES, and MS systems. We have found that for our use, these percentages of nitric acid, HCl, HF, ammonium hydroxide, and detergent are particularly useful. If you have any questions about rinse solution composition, you can contact our chemists, or reach out if you would like to look into formulating something especially to target out the washout issues you see in your lab. Thank you for spending your time with me today, and I hope that you were able to pick up a tip or two to make washout less of a problem. I also hope that you take advantage of our great technical resources on our website shown here. Thanks again.